Hi everyone, this is Saptarshi here and I welcome you back to our course on machine learning using Python. So we are in the unsupervised segment for quite some time and we have looked at different variants of clustering algorithms. So today we are going to look at another set of methods called as dimensionality reduction, and among those dimensionality reduction techniques which are there, we are going to concentrate on principal component analysis, also known as PCA. Okay, so this is one of the very popular algorithms which is used by the machine learning community. So we'll start by looking at the basic motivation of dimensionality reduction. We will look at the math behind dimensionality reduction in particular to PCA. Then we will look at an illustration using one of the most used datasets, Iris. And in the remark segment, we will look at where generally PCA is used and what are some of the alternative techniques of PCA. All right. So what are dimensions? So as you remember that all data sets, we represent by rows and columns, right? So, these are called as your features and these are called as your observations, right? So generally when we call about dimensions, we are mostly concerned about the features or the columns, all right? And now the question is that why do you need to reduce the dimension? Okay, so you can read up, you can search by the term named as cars of dimensionality and look at some of the very important problems. However, to give you a summary, all algorithms are generally represented in terms of time complexity and space complexity. And this time complexity and space complexity is represented in terms of M, or the number of columns, and N, the number of observations. Okay. So if in some way we can reduce M significantly, the algorithm will be definitely efficient in terms of time and space. Another important thing is that we want to visualize or interpret the data. So if you have any time more than 3 dimensions, and which is normally the case, right? You have now thousands of features. How can we reduce it to 2 or 3 features so that we can visualize the data? Okay. And the next question is that, is it different than feature selection? Okay, so let's say that your original data has attributes like this, right? So you have A1, you have A2, then you have AK, and finally maybe you have total M observations as we are telling, right? So you have AM observations, okay? And in feature selection, what happens is that you select some of them. So maybe you select A1, maybe you select AK, maybe you select AM. Okay, and the objective is that you do not compromise much on the information content in the original data, right? So you want to select feature so that the information content is not reduced much. In case of dimensionality reduction, what you do is you do not deal with A1, A2, AM anymore. Rather than that, you create new set of features. Okay, so these features maybe I will call as Z1 to Zm or Zp. Okay, now this P should be much lesser than M. Okay, however, please note that feature selection deals with original features, whereas in dimensionality reduction techniques, you work on newly transformed feature space. Okay, all right. So your original data or input data can be thought formally in this form. So x11 actually represents the value of the first feature for the first observation, and xnm actually represent the value of the last feature for the last observation. Okay, so your n are your observation and m are your variables, features or attributes. In PCA, what we want is we want to create new variables as we discussed, and they should be created such that they are linear combination of the original variables. Okay, so we'll understand this in more details pictorially very soon. Okay, and how should be the form of these new variables? So I can represent this as a vector okay, and I can call this as x1, right? So this vector I can call this as x1, and this vector again I can call this as xm, right? So what I want is that my newly created feature should be linear combination of such vectors, right? So it should be phi1 into x1 plus phi2 into x2 plus phi m into xm. Phi1, phi2, phi m are scalar quantities, right? So these are constants. And Z1 is one such newly created feature. We want to create such P features. Okay. All right. So what should be properties of such newly constructed features? We want to preserve the variability of the data. So this is the most important thing. And so we want to find linear combination of original features such that they explain the maximum variability. Okay. Such combinations are called your principal components, right? So from this, the name principal component analysis is derived. One property of the components are that they are uncorrelated to each other, which is technically called as orthogonal. And one important property is that these components has an order involved. So the first principal component explains the maximum variability, the second explains the next highest, and so on and so forth. Okay, now let's try to understand this with a simple example. Let's say you have data in 2 dimensions, and to understand how they vary with each other or what is the variability in the data, we represent them in a scatter plot. Okay. Now, if we want to find out any axis or any dimension along which the variability of the data is maximum, probably you can understand that that will be somewhere like this, right? Somewhere in this direction, right? So indeed it is in this direction. Okay. And now if we try to do this, we now think that okay, we are not going to represent the points like x y couple. We are just going to represent them by one value. What we can do is we can project this. Okay, we can project this in this dimension, okay, like this, and we can represent. So each of this becomes a point on the line rather than in 2D plane. Okay. So, but please understand that this will not represent the complete variability. So there will be some residual variability, and we will try to find a direction which is perpendicular or orthogonal to this direction where the residual variability is maximum. So maybe, this will be the dimension for the same. So once you represent the data in this dimension, right, in one dimension, it may look like something like this. And if you represent the data same way, if you project them here, maybe you will get something like this. So here, among its first principal component, if I call this as your first principal component, the variability is more, and second principal component, the variability is less. Okay. So instead of using my original axis, what I may want is I may want to rotate my axis so that my axis now aligns with the variability directions. Okay. So it can be something like this, right? So one axis is now along this direction, okay, and another direction or another axis is along this direction. Okay. So basically this is what actually you want to achieve through principal component. All right. Now to fully capture the variability, actually we need m principal components, right? So if you remember that you have m features, and what we are saying now is to completely capture the variability, we need m principal components, right? So one obvious question is, then where is the reduction, right? So what we can do is we can draw a graph like this. Okay. So where actually, we find out that what is the percentage variability explained by the first principal component, then what is the percentage variability explained by the second principal component, and I actually add it up. Okay. So this is actually cumulative explained variance of the principal components, and I can think of that maybe somewhere 0.9698 is good amount where I can stop. So maybe originally you actually had 400 features. However, when you are at 150 dimensions, so you have actually done away or eliminated 250 features, you are able to explain still 98% of the variability using this 150 principal components. Okay, all right. So now let's look at some of the mathematical intuitions, right? So the variability of the data set is represented by the covariance matrix, which is a square matrix, right? And you can, from linear algebra, you know that a square matrix can be broken down into eigenvectors and eigenvalues. Okay, so I will explain this in more detail. So basically, you have a matrix like this, and then you have a vector, then you have a scalar quantity and a vector. So essentially what we are telling is that eigenvector is a vector. If we multiply that with the covariance matrix, then it is equivalent to multiplying that vector by a scalar quantity. Okay, so if we can find such vectors, we call this as eigenvectors and eigenvalues. All right, but please understand that there is no one eigenvector or no eigenvalue. Rather, there will be a series of eigenvalue and eigenvectors. Okay, all right. Now let us look at a further intuition. So generally, a vector is represented by, or an observation is represented by a vector. Okay, and in your computer graphics, okay, so you apply different type of transformation on this point. So you can apply something like translation, and then you can apply something like rotation. Okay, and what happens is that these points gets changed. So this point gets changed, and maybe this goes somewhere here. Okay, and how do you explain this? So basically what you do is you have something called as a transformation metric. Okay, and this transformation metric you multiply by your original vector. Okay, that is the original point, and if you multiply this, you get a new vector. Okay, you get a new vector which represents this new point. Okay, so this is the idea of transformation. Now let's try to understand this in context to the eigenvalue and eigenvector that we discussed. So then actually what we are saying is that eigenvalue or eigenvector is such a special vector such that if you have a transformation matrix, okay, and if we apply that on the vector, it doesn't change the vector. Rather, it just scales the same. Because if you remember, we just have an effect of lambda, which is a scalar quantity, right? So that means that vector somehow understand some of the intrinsic characteristics of that covariance matrix. So this is the most important philosophy of the eigenvectors, that covariance matrix, which can be think of a complex composite transformation having scaling, rotation, reflection, many other things. Okay, if that is applied on the vector, that doesn't change the vector, because that vector somehow understands or somehow resonates with some characteristics of this transformation metric. Okay, all right. So now let's continue and understand this with the example of iris. Okay, so you are now well familiar with the data. So you have these four features, okay, which are your independent variable, and this is your class variable. Now, as you know, this is an unsupervised technique. We are not going to do with anything with the class, right? So your first step is looking at the variability of the data, which is represented by the covariance matrix. Okay. Your next step is now to find out the eigenvectors and the eigenvalues. Okay. So your eigenvectors will look like this. Okay. So as you remember that if there are four features, then you will have four principal components. So basically you have four eigenvectors. Okay. And then every eigenvector has a corresponding eigenvalue which is represented by lambda, which we have already discussed. So maybe the eigenvalues are like this. So please note how the value changes. Okay, so you can see that the first value is the maximum and then slowly it goes down. Okay, and basically these also tell you that how or what percentage of variability is explained by each of the eigenvectors. Okay, so if you actually plot them, okay, so the first principal component actually explains around 75 or 76% of the variability. The next one explains somewhere more than 20. So using two principal components, you can actually explain 96% variability of the data, okay, using your first two principal components, right? Now essentially what you do is, so you just select your first two eigenvectors, right? If you see, you are not using all the eigenvectors, you are just using the eigenvectors which explains the maximum variability. Now how do I transform my data metric? So what we do is, we just multiply your original data with this W got from or derived from these eigenvectors. Okay, so if I do that, I will get a matrix like 150 into 2 dimension, right? And now look at the linear combination. So basically when you look at this first eigenvector, okay, so this is your first principal component, which is nothing but 0.52 in the sepal length minus 0.26 into sepal width plus 0.5 into petal length plus 0.56 into petal width. Okay, so this is your linear combination, which is your first principal component. All right, and you can see that Y captures not 95%, actually more than 95% variability of the data. Okay, so your dimension is reduced by 50% and still you hold 95 or 96% variability of the data. Okay, and if you plot this, what can happen is, with the principal components and then you color it, you see that you have not used a class level, right? But even without that, you can see that this principal component somehow can separate the flowers well. Okay, all right. There is another term called as inverse transform. So this is an example from the Aurelio Gueron's book. So from the MNIST data set. So MNIST data set actually has 784 features. Using your principal component, what you can do is you can reduce them to 150 features. Okay, so you can understand that this is quite a lot of reduction. Now from this 150 dimension, actually you can apply inverse transform and go back to your 784 dimensions, right? So if you have original data like this, some samples, and if you take it to 150 dimensions and then again do an inverse transform and go to 784 features, this looks something like this, right? So you can very well understand that there is no much loss in information, right? All right. So when to use PCA? So there are some questions. Okay. So questions are, do you want to reduce the number of variables but aren't able to identify variables to completely remove from consideration? So basically you are not able to select some feature or eliminate some feature. Now, do you want to ensure that your variables are independent of one another? So when you are trying to find those variables, so then as it is orthogonal, they will be independent of each other. And then, are you comfortable making your independent variable less interpretable? Okay, so as they are linear combination of the original features in your business domain, this will not have much semantics or much meaning. Okay, so if your answer is yes to all these three questions, PCA is a good method, and particularly this question is the most important question. Okay, so if you answer no to question 3, you should not use PCA. All right. Now, some more things about PCA. So as this deals with variance of the data, the scale of the data will be a key feature. Okay. So as example, age column may have variance of 5.6 and salary may have variance of 5,000. So in such a case, we need to standardize the data. Okay. However, please note, instead of correlation metrics, if instead of covariance metrics, if we use correlation metrics, then we don't need to standardize because correlation is scale invariant. That is, it is already scaled. Okay. Now there are some techniques like incremental PCA, which uses concepts like mini batch and batch, because for some cases it may be difficult to load the entire data in training. Okay. There are some other interesting techniques named as kernel PCA, multidimensional scaling, latent discriminant analysis, okay, or linear discriminant analysis. So which are other techniques for linear transformation, which we will discuss in our next class. Okay. So thanks guys for watching this video. And if you have enjoyed this, please like and subscribe. Feel free to put your questions and we will try to answer them to best our abilities. Thank you so much, guys.